Welcome students to the lecture 2 on sensors. In our lecture 1, we discussed the classification of sensors. We understood what are passive sensors and active sensors. We also discussed some important examples of passive and active sensors. And now in this lecture 2, we are going to discuss the strain and pressure sensors in detail. Students, let us now try to understand what is a strain sensor. Usually, we employ piezoresistive and piezoelectric principles to sense strain. Now, let us try to understand what is piezoresistive effect. Electrical resistance changes when the material is mechanically deformed. This is what we call piezoresistive effect. So if you subject a material to strain, its electrical resistance changes. Let us understand this in detail with strain gauge sensor. So obviously we understood strain gauge sensor employs piezoresistive effect. So we define it like this. A strain gauge is a resistive elastic sensor whose resistance is a function of applied strain. Now you see in this figure, there is a metallic grid pattern, what we call resistor. Now this resistor is bonded with this elastic carrier, the white one, what you see in the figure is called elastic carrier, also called as backing. The backing in turn is applied to the object for which stress or force should be measured. We are calling in this figure it as specimen. So we have this resistor bonded with backing. Now this in turn is applied to the specimen. Usually this metal grid what you see here or the resistor is made up of alloys like constantan and nichrome. Another important thing is that the resistor and the backing should be thermally coupled. In the sense, the thermal expansion of this resistor and this backing should be matching. So this is how a real-time strain gauge looks like. Now how do you sense strain with it? Students, you recognize this as Wheatstone bridge network. So there are 4 resistors in this network. You see, in place of the 4th resistor, we place this strain gauge. Now as an example of active sensor, we already discussed this. And now active sensors always require an excitation signal. So this current passing through this network is the excitation signal. Now this strain gauge is applied to the specimen whose strain is to be measured. So now the effects of temperature, if any, can be minimized by using another identical unstrained strain gauge in the bridge as comparison. So if I want to minimize the effects of temperature, even I replace R2 with another identical strain gauge. So now we have this piezoresistive effect working here, as we already mentioned before. We are applying the strain gauge to the specimen. The strain caused in the specimen is changing the resistance of this metallic grid. Now when the resistance changes, the excitation signal is getting modified, or the current in this network is getting modified. And now this piezoresistive effect is expressed through something called gauge factor, SE, of this conductor. So we have a very important relation by which we can measure the strain. The change in resistance dr by r is equal to SE into small e. Small e stands for strain. So the gauge factor SE is nearly equal to 2 for many materials. And now we can go for a semiconductor material to make this grid pattern. Now for a semiconductor gauges, it is between 40 and 200. Students, now let us try to understand pressure sensor. So now, how to measure pressure? Using these pressure sensors, we usually measure the pressure of gases and liquids. Now we can use these pressure sensors to know the fluid flow, the speed, the water levels, altitudes. Students, I was mentioning in my lecture 1 about the pressure sensors in aircrafts or rockets. Now, how do they function? This is one simple sketch indicating the basic principle where we employ piezoelectric effect to sense the pressure. Now in this diagram, you see there is a diaphragm. Diaphragm is nothing but a thin metal film, and then you see this is the pressure to be measured. So you send the gas or the liquid whose pressure is to be measured through this inlet. And now there is a fixed pressure on the other side of the diaphragm. So when I send the gas or a liquid here, due to the pressure difference on either ends, on either sides of this diaphragm, the diaphragm starts to oscillate or vibrate. So when there is a deformation in the diaphragm, this deformation, the mechanical deformation in the diaphragm, is carried to a piezoelectric crystal. Usually we use a barium titanate piezoelectric crystal in such sensors. There are many other materials which exhibit piezoelectricity. Piezoelectricity is something like this. You take a crystal, you subject it to mechanical strain. Now there are electrical oscillations generated from the crystal. So you subject a material to mechanical vibrations, electrical oscillations are generated. That is what we call piezoelectric effect. So whenever this diaphragm moves, the crystal here oscillates. Whenever there is a mechanical deformation in the crystal, there are electrical oscillations, as I said, so there is a voltage output. So the pressure is sensed as an electrical output. You are calling such a sensor as a piezoelectric pressure sensor. This is one way of sensing pressure. And remember, the piezoelectric voltage developed is proportional to the pressure on the crystal. More is the pressure on the crystal, more is the voltage developed. Now let us see another kind of pressure transducer or pressure sensor. Capacitive pressure transducer, we call this as. Students, to measure pressure, we use a barometer. So this is what we call aneroid barometer, which employs this capacitive pressure transducer. Again, we see the pressure to be censored being sent through this inlet. Now this is the diaphragm, and now there are two plates of the capacitor, one linked to the diaphragm. Now this is a parallel plate capacitor, you can clearly see here. So now when I send the pressure, or when I send some liquid or gas into this chamber, due to the pressure difference on either sides of this diaphragm, so the diaphragm starts moving, or there is a mechanical deformation in the diaphragm. So this movement of the diaphragm will cause a change in the capacity of this capacitor, because we learned the capacity of a parallel plate capacitor C is equal to epsilon naught A by D, where A is the area of the plates, D is the distance between these two plates. So whenever the diaphragm moves, the distance between the two plates of the capacitor changes. So the capacity of this capacitor changes, which can be detected with the help of a detector here. Now the displacement of this diaphragm can also be censored by a displacement transducer. And for most of the purposes, we usually prefer steel diaphragm. A thin steel film is used as a diaphragm. Even a ferromagnetic material can be used as a diaphragm. Ferromagnetic material in the sense iron, cobalt, nickel can also be employed for this diaphragms, but the principle will be a little different to sense the pressure. Students, remember, if you are using an earphone or a mic, there are such diaphragms inside, and piezoelectric effect plays a major role. Now we again try to understand this piezoresistive pressure sensor. Previously we understood the strain sensor. Now this is a pressure sensor using the same strain gauge. The principle is same, piezoresistive effect. What is piezoresistive effect? I remind you again. The mechanical deformation in a material changes its resistance. So the principle is again simple here. We have a strain gauge here on this diaphragm. So this is the diaphragm. So we are applying pressure here. Because there is a pressure difference on either side of this diaphragm, the diaphragm moves. There is a mechanical deformation in the diaphragm. Now this diaphragm is coupled with this strain gauge. So the resistance of this metal grid on the strain gauge changes. Now that modifies this excitation signal, by which you can estimate the pressure applied. So this is a simple pressure sensor employing strain gauge. So the displacement of the diaphragm again is being censored by this strain gauge. Students, in many engineering applications, we use these tactile sensors. Tactile sensors are a special class of pressure transducers which are characterized by small thickness. Especially in mechanical and civil engineering, these sensors can be used to study forces developed by fastening devices and all. Students, you see in this diagram very thin films of PVDF films we call them as. So good tactile sensors can be designed with piezoelectric film like polyvinylidene fluoride. PVDF stands for polyvinylidene fluoride. So you see in this diagram, this is one polyvinylidene fluoride film, a very thin film. And then we have a layer, an intermediate layer here, the pinkish one. We call it as an acoustic coupling. And now the upper layer is again a PVDF layer. So in this figure, it appears to be a thick one, but it is as thin as this. We employ these pressure sensors or force sensors in many engineering applications. Students, see how it functions. This is another best example for an active sensor. So now you already understood what is piezoelectric effect. The mechanical vibrations are converted into electrical oscillations. The vice versa is also possible. So now I give an AC input. So the electrical oscillations to the lower film, the lower PVDF film here, as you see. And now this acoustic coupling layer we call should be as soft as possible, so that when I subject this film to electrical oscillations, there are mechanical vibrations developed. These mechanical vibrations are coupled onto the upper film you see here, which is again PVDF layer. So when I subject this upper film to, or the mechanical vibrations carried onto the upper film, they in turn again create the electrical oscillations, the inverse piezoelectric effect, and these electrical oscillations are sensed as output. So we have an input and then we have an output here. The electrical input and the output is also electrical. Now, until there is no pressure applied on the upper part of the film, the electrical output almost matches with the input. And remember, the sensitivity of this sensor obviously depends on this coupling layer, as I already mentioned, the softness of this coupling layer. Now imagine some pressure is being applied on the upper layer. So the pressure applied on the upper layer will obviously damp the mechanical oscillations that are communicated from this layer. So there will be a change in electrical output, and this electrical output is fed into an amplifier which amplifies the signal, and that signal is again sent into the demodulator, and that demodulator is very sensitive to the amplitude and phase of the signal. So the amplitude and phase of the output signal will determine how much pressure is applied on this upper film. This is how this tactile sensors work. Remember, in many of the touch sensors, we'll be using such tactile sensors. Like in case of your mobile phones, we use this thin film pressure sensors. Or you take any touch screen of your laptop or an inquiry kiosk, we'll be using such tactile sensors, which are characterized by very small thickness. Students, in this robotic arm you see here, or the prosthetic arm or the touch screens, as I just mentioned, we are using these tactile sensors. You see, this rubber skin, we call it as, for a robot or in robotics, we use these PVDF films embedded into this rubber skin, and the electrical signals produced reflects the movement of this elastic rubber. So when I'm trying to catch a ball, there is a mechanical deformation, and this rubber skin responds because there are tactile sensors in this. So this rubber skin responds to the movement. Now the same is the principle we use for prosthetic arms, and these tactile sensors are used in screen displays like this, keyboards, and many other devices. So now let us try to understand what are magnetostriction sensors. The thing is, we have some very important class of materials which exhibit magnetostrictive effect. For example, nickel, iron, permalloy, and terphenol D. The chemical formula is given there. They convert magnetic energy to mechanical energy and vice versa. So as a magnetostrictive material is magnetized, it strains. Now let us concentrate on this figure. We have a ferromagnetic material. You can see ferromagnetic materials are exhibiting this magnetostriction. Nickel, iron, all these are ferromagnetic materials. So imagine I have a ferromagnetic rod and I subject this rod to a magnetic field by passing current through this coil. Now we observe a change in the length of that particular rod. So whenever a ferromagnetic rod is subjected to magnetic field, there is a strain caused in it. This very effect is called Joule's effect or magnetostrictive effect. And the vice versa is also possible. Now look at the figure B, where the strain can be converted to magnetic energy. Say, for example, I take a ferromagnetic rod and I try to apply some strain to it. We try to bring a strain in that rod by applying some force. So now what happens? Potential difference is developed between these two ends. So the strain can be converted to magnetic energy, as you see here. This is called Villary effect. So the previous one is magnetostrictive effect, and this is called magnetoelastic effect. You cause a strain in the ferromagnetic rod, we observe a change in magnetic flux resulting in current passing through this coil. Villary effect, we call this as. Basing on these two principles, the magnetostrictive effect and magnetoelastic effect, let me now explain you how an active magnetostrictive sensor works. This is the simple design of the magnetostrictive sensor, an active magnetostrictive sensor. Now in this diagram we see a C-shaped ferromagnetic sensor core. This is all the core, and now there is an excitation coil, as you see here. This is the excitation coil, and now there is an sensing coil, and now when I try to pass some alternating current in this excitation coil, obviously due to mutual induction, now this sensing coil has some output, power output. But now imagine there is a target here. The target is just close to this sensor. Now, this whole thing is a sensor. Now that this is a target. As the target is close to this sensor, there is a flux linkage, as you see here. The magnetic flux due to the current passing in this coils is linked to this target also. So now when I strain the target, so there is a change in the stress. Obviously, there is a change in the magnetic flux or the permeability changes, and now that is detected as a change in the voltage in the sensing coil. On this very principle of Villere effect, this active magnetostrictive sensor is working. So how do we classify this as an active sensor? Obviously, active sensors always require an excitation signal. So we are trying to give an excitation signal, and there is a modified signal being sensed by this detection coil or sensing coil. That is how a magnetostrictive active sensor works. We also have magnetostrictive passive sensors where you just strain this target and there is a change in the magnetic flux giving us an electrical output. Right. So magnetostrictive is another important phenomena for sensors. Now let us discuss a little on optical fibers. So we are trying to end this discussion on the sensors or the pressure sensors with this optical fiber sensor. But before I teach you what an optical fiber sensor is, let me first give you a knowledge on total internal reflection. What is total internal reflection? Imagine there are two different media. This medium is denser and this medium is rarer. By the refractive indices, you can identify that. So here the refractive index of this medium is 1.5 and the refractive index of this medium is 1. So this is optically denser medium and this is rarer medium. Always when light tries to pass from denser medium to rarer medium. Imagine, take this green color ray. When light is passing from denser medium to rarer medium, it bends away from the normal. So light bends away from the normal. Now if I try to increase the angle of incidence, now at one particular angle called critical angle, the angle of refraction is exactly 90 degrees. You can see this red color ray, the angle of refraction is 90 degrees. So the ray just grazes the interface separating the two media. Now what if I try to incident light at an angle greater than critical angle? So now what happens? Light gets reflected back into the same denser medium. You can see the blue color ray. So when light is incident at an angle greater than critical angle, it gets reflected back into the same denser medium, and this is what we call total internal reflection. Remember, total internal reflection is the main principle in the working of an optical fiber. So today all the high speed communication we are having is just due to this fiber optics communication. So let me show you how this light rays propagate through an optical fiber. So obviously, because total internal reflection is observed when light passes from denser medium to rarer medium, now I have an inner core which is denser. So this is how an optical fiber looks like. We have a denser core and now there is an rarer medium here covering that. We call this as a cladding. So this layer is cladding, this layer is core. So when I try to incident light, and if it falls at an angle greater than critical angle, it gets reflected back into the same medium. So light gets confined only to this particular core and gets propagated. So this is how we can communicate light through an optical fiber. Obviously, the energy loss will be less when compared to any other dielectric cable. So that is the reason we find a number of applications for optical fibers, especially in high-speed communication techniques. So now what if I bend this particular optical fiber? So we call these things as bending losses. Not going deep into the subject, but just to give you an idea, if there is a bending in the optical fiber, imagine, such that when light is incident at the interface of core and cladding, okay, with an angle other than critical angle, the angle may be less than critical angle. For example, in this case, as you see here, it is just 50 degrees. So it may happen that the light may get lost into the cladding. Just because there is a bend in the fiber, the light is getting lost into the cladding. So now there are such bending losses in an optical fiber. To get you a clear understanding, let me show you. You can see this particular region where light is getting lost to the surroundings. Okay, so this is how you get these bending losses in an optical fiber. So whenever there is some bending loss in an optical fiber, there is a change in the intensity of light coming out of the fiber. We take this principle and frame. Let us understand how a fiber optics pressure sensor works. Now let me show you in this figure the block diagram of a pressure sensor, fiber optics pressure sensor. You see a laser source. So this is the laser source we have. The light coming from the laser source is sent on to a beam splitter. So some part of the light is reflected in this direction and some part of the light is transmitted in this direction. Now both these light rays are fed into the optical fibers. There are two optical fibers you see. One is the blue colored one, the other one is the red colored one. So now the light passing through this optical fiber is subjected to some pressure changes or temperature changes. So we call this as a sensing cable. Now the other optical fiber you see here is not subjected to any change. So this is what we call a reference cable. So this is the sensing cable, this is the reference cable. So the light coming from these two cables is finally fed into a comparator. A comparator compares the two light rays. So we may catch the interference pattern and analyze the output, whatever it is. So finally, we are able to distinguish the change caused due to the pressure applied or any other temperature changes caused in this cable. So usually in pressure sensors, when you try to apply pressure, we have this corrugated blocks, we call them. For example, I try to show you in this. So these are called corrugated blocks. So the optical fiber, the sensing optical fiber is sent through these two corrugated blocks. So now when pressure is applied on this upper block, now the fiber is bent. So when the fiber is bent, the light passing through this optical fiber, exhibits a change in the phase or the intensity, which can be analyzed in the comparator. So when the pressure is applied on the sensing fiber, the comparator detects the distortion from the interference pattern obtained. So this is how a fiber optics pressure sensor works, and with this I end my lecture 2 on sensors. So in lecture 2 we learned how a strain sensor or pressure sensor works, the various principles on which these two sensors work. Thank you.